All right, welcome everybody. I'm really excited to begin this journey through Calculus 2 with you. Today we're going to be starting our first section of what I would say is new mathematical content, or at least some of it is new, specifically from Calculus 2. The previous lectures were just some review from pre-calculus and Calc 1, and then just an introductory lecture to kind of let you know how things are going to run. But today we're going to talk about inverse functions and their derivatives. So this is section 6.1. Let me pull up the slides here and then we'll begin in just a second. This is a section that technically we cover in Calc 1 here at SMC, but I tend to like to cover it again in Calc 2 anyway, because a lot of times professors can't get to it in Calc 1, and it doesn't hurt to just kind of review things anyway and, when it comes to inverses and especially when it comes to derivatives of inverses. So let me go ahead and get started. Give me 1 second. Yeah, there we go. Okay, so here's a quick overview of what you can expect today. We're going to review what functions are very quickly. Then we're going to talk about one-to-one or injective functions. Then we'll talk about inverse functions. We'll get an important result about certain functions that tell us that we know that they have inverses. Then we'll talk about the horizontal line test, graphical interpretation of inverse functions, the cancellation equations, and then we'll get to the calculus part, derivatives of inverse functions, and the important inverse function theorem. One thing I'll mention here is that I'm going to try to move through this stuff fairly quickly, mainly because you are supposed to cover that in pre-calculus in pretty great detail. So I won't dwell too much on those topics, but it's really good to review them anyway, because inverse functions can always feel a little bit, I don't know, weird if you're not used to using them a lot. All right, so let's get started. First off, just a review of what a function is. So if you will recall, a function is just a rule that assigns to each element x in a set D sub f called the domain, exactly one element f of x in a set called R sub f, the range. So in a very, very intuitive way, functions are basically mappings from one place to another place. So you've probably seen this picture before when your teacher talked about functions. This is like the canonical picture. Here's the domain of a function f. Here's the range of a function f. And what f does is it takes things from over here and maps them over here. So that arrow is quite literally the function f itself. And you can see here that it takes this point x and it maps it to this point over here, which we call f of x. So just some other definitions. The domain of a function is the set of all the input elements that work. So in other words, this is the set of all the things that the function can actually process. If the function can't handle certain things, certain elements, certain numbers, then those are not things that we want in the domain of the function because they'll break the function. Once you have a function f, the range of f is the set of all the possible outputs. So the range is everything that the function can spit out. And then in comparison, there's another set that you may not have heard about from your previous instructors called the codomain. So the codomain of a function is basically where the range lives. So for example, if you think of the function x squared, oops, here we go, f of x equals x squared. Well, the range of that function is the interval 0 to infinity. That's the range of x squared, right? And you can kind of picture the graph of x squared. And the range is basically everything here and up, right? So the range is 0 to infinity. The codomain would be the entire real line itself. So the codomain is kind of like the space where the range lives. That's the idea. All right, some more intuition. And again, if you took me for pre-calculus or Calc 1, we talk about this in great detail, but the concept of a function is a very general concept. So a function is very much just like a box that transforms objects into new objects based on some rule, and we usually call that rule f, or whatever letter or name you want to give it. So functions are kind of like boxes, and they're transforming things into other things. The only requirement that our box is to make our box a function is that it can only spit out one thing at a time. And we call that thing that it spits out f of x. That's the thing that comes out of the box. So that's what this picture is kind of showing you here. And the reason I like to emphasize this is there's a distinction between the function f and the output of the function f. And in my experience, students that struggle with functions, really it boils down to not being totally comfortable with the notation, which we're going to talk about in a minute. But generally speaking, the idea is that you take an object, you drop it into this box, this rule gets applied to that object, and then what comes out is the transformed object, transformed according to that rule f. All right, so here is the notation. I'm hoping that you all are really comfortable with it, but if not, we're going to review it right now. Making sense of this notation can save you a lot of headaches, so we'll go through it carefully right now. The symbol that is inside the parentheses here, no matter what the symbol is, that is the input. So this X that you see here, that's just a placeholder that represents the thing we're putting into the box. So it could be X, it could be A, it could be A plus H, it could be X minus 2, it could be 3X plus 1, it could be sine of X, it could be anything. Basically, this is just a placeholder for what you're putting in the box. That's what it's for. This symbol right here, that symbol is the name of the function or the rule of the function. And you can really think about it as like a sticker on the side of the box that says what the box does. So it's like, what happens when I put something into this box? Well, the sticker on the side says it's going to do this when you put something into it. That's what this letter is representing. And then here's the critical idea. The critical idea is this. The entire symbol itself represents the output of the function. That's the output of the function. It's not the function, it's the output of the function. And that's why this picture is so handy. You take X, you drop it into the box, it gets F'd up, and then what comes out is f of X. That's how it works. So remember, when you see the symbol f of X, think of it as an output of a function, not the function itself. Okay, so here's a classic example, just a simple example using these ideas that I was talking about. Here we have the function 3x plus 1. X is the input. X is what we're putting into the box. F is the rule that is given by this sentence. So quite literally, this letter F here is representing this sentence. So when I say F, I mean multiply by 3 and then add 1. That's what F means. So what does this function do? It takes your input, it multiplies it by 3, and then it adds 1 to that result. That's like the sticker, right? So F is the sticker on the side of the box that says, hey, this box multiplies by 3 and then adds 1, okay? That's what F represents. Now what comes out of the box? What comes out of the box is your input multiplied by 3 and then having 1 added to it. That's the output of the box, F of X. F of X. All right, so that's the idea. Now, let's talk a little bit about inverses. So here is the big question. The question is this, and I ask you this question. If we have a function f, does the process of working backward from the output to the input constitute a function itself? So kind of like if we went backward, if we tried to take the if we tried to take the output and put it through some box, don't even know what to call the box, will we get back x, and is that process a function? Does that constitute a function? So what I'm going to do now is I'm actually going to throw the thinker up here. Here you go. So in my lectures, what I like to do is I like to throw up some of these emoji just to get you to kind of think about some of the questions that I ask or some of the examples that I ask. And so what I'll do is this. I'll throw this out, and what I mean is I just want you to spend a moment thinking about this question and seeing what you think the answer is. So think about it for a minute. Okay, next what I'm going to do is I'm going to show this other emoji. So this is the speaking emoji. And what I want you to do is I just want you to say something out loud about what you were just thinking about when you were trying to answer this question. Anything at all. The idea is to give your brain that feedback of yourself speaking something out loud. You don't have to talk to anybody, you can just talk to yourself. But if somebody's around, you can talk to them, you can talk to your dog, your cat, your kids, your friends, your family. Just say something out loud about what you were just thinking. All right, and now let's talk about it together. So, does the process of working backward constitute a function? Well, the answer is sometimes, but not always. The way that I like to think of it intuitively is, is there a process, or I should say this, can you think of a process where if you tried to reverse it, you would not get back what you started with? Or maybe is every process reversible? Because I wouldn't say that every process is reversible. So, and generally speaking, sometimes we can invert a function, but not always. So that function has to have certain properties in order to be invertible. And that's where this definition comes in. So a function is a function is invertible if and only if it is one-to-one, or injective is another word for it. So let's see what that means. A function is called one-to-one or injective if it never takes on the same value twice. That's what it means to be one-to-one. It never takes on the same value twice. That means that your function will not output the same value twice. So for every distinct 2 points in the domain, no matter what, the outputs will never be equal. That's what it means to be one-to-one. A good counterexample is x squared again, right? It's an easy one to think of. F of x equals x squared. This function is not one-to-one. And the reason is that there are different inputs that will lead you to the same output. For example, if I put in the number, let's say 2. If I put in the number 2, I get out the number 4 under the function x squared. But also, if I put in the number -2, I also get out the number 4. So the function is taking on the same value twice. If I put in 2 different things, I'm getting the same output, right? So that means it's not one-to-one, which means it's not invertible. All right. So now what is the definition of an inverse function? Here we go. So let's say we've got a one-to-one function, so we can actually invert it, and it's got domain A and range B. Then its inverse function, which is denoted by f to the -1, and it's pronounced f inverse. Well, that inverse function has domain B and range A, and it's defined through this equivalence relationship. So what we're saying is that f of x equals y if and only if f inverse of y equals x for any y in B. Okay, so what I want you to do for just a moment here is, frankly, just ponder this, read this definition, and think about it for a minute, and then we'll make it more intuitive in a moment. All right, so let's talk about it together, and then we'll look at a picture to see how these things kind of work. But intuitively, what inverse functions do is they undo the process of an original function. So for example, if the original function says to multiply by 3 and then add 1, the inverse function will say to subtract 1 and then divide by 3. So that's what inverses do. They quite literally invert the process. One thing I want to point out is notice that the order and the elementary operations are inverted. So when I said multiply by 3 first and then add 1, if I want to reverse that process, I'm going to subtract 1, then divide by 3. So the order and the operations are inverted. Here's kind of a picture of what's going on. So it's an alteration of that first picture I showed. But here, let's say we've got the domain of f, and here's the range of f. And remember, what does f do? F takes points over here and maps them over here to the range. So it takes points like x and sends them to f of x. Well, the inverse function, if it exists, if you have an invertible function, it goes backward. It takes these things and sends them here to the original domain of f, right? So here it's like if I take the point y and I put it through the inverse function, I'll get the point x, because f inverse of y is equal to x. Why is f inverse of y equal to x? Because f of x is equal to y. So it's quite literally this like inversion process. That's the idea. Okay. So a couple of important notes. One thing, inverse functions switch the domain and range of the original function. So the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. So domains and ranges are switched, and you can see that in this picture, right? Here, B is the domain of f inverse, and A is the range of f inverse. Everything's getting switched. The other thing is this. So this is an important notational point right down here. That little -1 in the notation, f inverse, does not mean reciprocation. So this is a little bit of what we call an abuse of notation. We're kind of abusing the to the negative 1 notation, but we're abusing it for good reason. It actually turns out to be very, very intuitive to call it f to the negative 1. But I just want to make it clear that when you see that, we are not talking about division. So f inverse of x is not 1 over f of x. Kind of the same way that if you remember trigonometry, right? If you have something like sine to the negative 1 of x, that does not mean 1 over sine of x. That means inverse sine of x. But we use that notation to indicate an inverse. Okay, so let's try an example here. Let's say we have an injective function, a one-to-one function, so it's invertible, and we know three things. We know that f of 1 is 5. Actually, let me highlight it. Here we go. We know f of 1 is 5, f of 3 is 7, and f of 8 is negative 10. And what I want you to try on your own is this. See if you can figure out what f inverse of 5, f inverse of 7, and f inverse of negative 10 are. So think about it for 1 minute. All right, now say something out loud to yourself or to anybody, to your dog, whatever, about what you were just thinking about. How would you go about finding these values, f inverse 5, f inverse 7, f inverse 10, negative 10? All right, now let's talk about it together. This is the result. We know that f inverse of 5 is equal to 1 because f of 1 is equal to 5. So if I plug in the number 1 to my function f, I get out the number 5. Well, inverse functions invert things. They invert the domain and the range. So if I know that the output of 1 is 5, then I know that f inverse of 5 is 1. That's going to take me to the input that gave me 5. And the same thing for all the others. F inverse of 7 is 3 because f of 3 is 7. So f inverse of 7 is the number that f sends to 7, which is 3. And then lastly, same thing. F inverse of negative 10 is 8 because f sends 8 to negative 10. So f inverse of negative 10 is 8. There you go. All right, so that's how inverses work. They kind of reverse the order of things, right? How about this one? So try to work this one out on your own, and then we'll do it together as well. See if you can find the inverse of x cubed plus 2. First, think about how you would do it. All right, now say something out loud to yourself about how you would do it. Anything at all, just to give your brain that audio feedback. All right, and now try to work it out on your own. So break out a pencil or a pen or a whiteboard and see if you can compute the inverse of f of x here, and then we'll do it together. All right, let's do this one together. However process or whatever process you learned for inverting functions, you are more than welcome to use it in this class. I don't mind. I like to show the inversion process this way because I feel like, well, I'll put it this way. You might have learned to like change things to y and then switch x and y and then solve for y and then call it this at the end. You don't need to do any of that stuff. You really don't need to do any of that stuff. Just remember that if you're trying to invert a function, you're trying to solve for the input. That's what inverting a function means. It means you're going to take this result, which is the output, and you're going to solve it for the input, and that will invert the function. So what I mean here is you don't need to change the symbols of anything until the very, very end, and you don't need to like switch order or any of that stuff. Just solve for x. Take this equation and solve it for x. So here I go. What did I do first? I subtracted 2, and then I took the cube root of both sides so that I have x is equal to the cube root of f of x minus 2. The function has now been inverted. That is how it's been inverted. Because look, now I can put in the output, and it will tell me the input that sent me there. So the very last step is just to relabel things. Remember, these symbols are just placeholders for inputs and outputs. So the last thing I'll do is I'll just relabel things and say that, well, the inverse function of f does this. It takes a result, subtracts 2, and then takes the cube root. That's the inverse function of f. And that makes sense too, right? Think about what f does. F says cube the input, then add 2. F inverse says, subtract 2 from the input, then take the cube root. There you go. It's inverted, right? And then back this way. There we go. If you feel more comfortable replacing things with y and so on and switching, you're more than welcome to do that. It's just not necessary. It's not really necessary to do any of that. All right, let's try another example. So here's another function, 2x plus 1 over x minus 5, defined for all x not equal to 5. See if you can find the inverse on your own, and we'll do it together. So think about how you would start. All right, now say something out loud to yourself about how you would start this process. How are you going to start the inversion process? All right, now you try it on your own. See if you can calculate the inverse algebraically, and then we'll do it together in just a moment. All right, let's do it together. So just like I was saying before, all you need to do is solve for x. That's it. Take this equation and solve it for x. So I've got it typed up here all on one slide, and I'll just walk through the steps. First step is I'm going to multiply both sides by x minus 5, so now I don't have a fraction over here. The next step is I'm going to distribute f of x to these two terms. So I'll get x times f of x, and I'll get negative 5 times f of x. Remember, f of x is the output, so you treat it as its own symbol. That f of x is a single object. It's the thing that came out of the box, right? So it doesn't split up or tear apart or anything. It's just its own single symbol. That's it. And you can manipulate it as if it's a single symbol because that's what it is. Now let's remember the goal here. The goal here is to solve for the input. So the input is appearing right here and right here, right? Because remember, this is the output. F of x is the output. We're not solving for that. We're solving for the input x. So just like you learned back in algebra, if you want to solve for something, you need to combine like terms and get all of those somethings together, right? So that's what I'm going to do from this step to this step. I'm going to subtract 2x from both sides so that both of the terms with x in them are on the same side. X times f of x and 2x. There we go. Then I'm going to move everything else to the other side. Or I should say this, I'm going to move everything else to the other side. So I'm going to move this thing over to here, and that's where we get the positive 5 times f of x. Now the next step, I'm going to factor x out of both of these terms. Remember, this is x times f of x, and this is negative 2x. So I can factor an x out, and I get this. X times f of x minus 2. No change over here. And then the very last step is to divide both sides by f of x minus 2, and voila, that's what I get. So the function has been inverted. The function has now been completely inverted. Notice here, if I provide an output, it will tell me the input. There you go. That's exactly what inverting does. Now I can relabel things. So now that I've inverted the function, I'll just relabel it. I'll say f inverse of x does this. It does 1 plus 5 times the input over the input minus 2. And then here I just rearranged things. Just switched the order so that the linear term was coming first in the numerator. But that's the inverse. That's the inverse of it. So some cool things to take note of are these. For one, notice that the vertical asymptote of f is x equals 5. There's a vertical asymptote at x equals 5. And the horizontal asymptote is 2. So there's a horizontal asymptote of f that's equal to 2, right at where y equals 2, right? But now look at f inverse. In f inverse, those two things have been switched. So the vertical asymptote of f inverse is 2, and the horizontal asymptote is 5. And that's precisely because the domain and the range are getting switched by the inversion. So when you invert a function, the domain and the range get switched. That's why this vertical asymptote becomes a horizontal asymptote, and this horizontal asymptote becomes a vertical asymptote, because it's like the x's and the y's are getting switched. It's not the best picture, sorry. That's the idea. And that's one of the reasons we get this really, really nice test. So there's this test called the horizontal line test, and I'm sure that a few of you were like waiting to hear about this, right? Here's the theorem. A function is one-to-one if and only if every horizontal line crosses the graph only once. So in other words, if any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function, and so that function doesn't have an inverse. That's right. So basically think of any function that you can draw a picture of, right? And then what I'm saying is if you draw a horizontal line through it, does it touch the graph twice anywhere? If it does, the function is not invertible. Not invertible. So we'll use x squared. Here we go. X squared is another great example. Maybe I'll use some blue here. Okay, so this is the function f of x equals x squared. It's not invertible outright. It's not invertible. It's not one-to-one. It doesn't pass the horizontal line test. So if I try to draw a horizontal line pretty much anywhere, it touches the graph in two different points. That tells me that it's not invertible. That tells me that it's not invertible. There are ways to make part of it invertible. You just have to start restricting the domain. And I wanted to mention that because if you recall in trigonometry, when you were talking about the inverse trig functions, this is exactly what you had to do to even define the inverse trig functions. So think about the sine function for a minute. I'll draw one period. Sine function looks roughly like this. Right? It's not invertible. It's not invertible. It doesn't pass the horizontal line test, right? That touches in two different points. So outright, it's not invertible at all. But what you do back in trigonometry is you say, well, I would really like to be able to talk about inverting these trigonometric functions. And so what you do is you restrict the domain. And you did this for all three of the standard trigonometric functions. Oops, let me do this. There we go. So for sine, I actually need to draw a little more of it. Come back this way. There we go. So if you remember, for the sine function, you end up restricting the domain to be negative pi over 2 to pi over 2, right? So like from here to here. And if you restrict sine, oops, inclusive, there you go. If you restrict sine to that interval, then it's invertible. Then it's invertible, because then you'll only hit the graph one time if you try to cross it with the horizontal line. So the horizontal line test is great. The horizontal line test lets us determine if functions are invertible just by looking at them at a glance. That's why it's so nice. Okay, now the next thing I want to talk about is an important result, and we're going to use this result in this class, in about 2 sections, I think, 1 or 2 sections. Hopefully this is something that you talk a little bit about in pre-calculus, but if not, that's okay. We're going to talk about it right now. If your function is strictly increasing or strictly decreasing, then it is invertible. Strictly increasing or strictly increasing, then it's a one-to-one function and therefore it's invertible. The important part here is that it does have to be strictly increasing, or actually I should emphasize this. It has to be strictly increasing or strictly decreasing. What that means is it can never level out on an interval. It can never level out on an interval. There's a tongue twister for you. So for example, this function right here, sorry, that's not the best picture. Maybe I'll do something like this. There we go. That function, just by looking at it, I can tell that it's invertible. It's strictly increasing, which means it's always increasing. There's never a point where it dips down and starts decreasing, and there's never an interval where it levels out and remains constant. So for comparison, here's a function that is not invertible. I could do something like this. There we go. So this function is not strictly increasing, and therefore it's not invertible. There's a portion where it levels out and remains constant. In essence, it doesn't pass the horizontal line test, right? Because if I draw a horizontal line right through here, it's going to touch the graph at infinitely many points. So it's definitely not invertible. So this is just a really handy, really important result, that if you know that your function is strictly increasing or decreasing, then it's guaranteed to be invertible. We're going to use it when we start talking about the logarithm and the exponential function. All right, so now let's talk about the graphical interpretation. Hopefully you've seen this before, but if not, that's okay. Because the domain and range of an inverse function are switched from that of the original function, that literally means the inputs and the outputs are switched. inputs and outputs get switched. So graphically what that means is the x values and the y values on the graph are switched. And so what I have a picture of here is I have a picture of the function x cubed and its inverse function, cube root of x. I'm going to zoom in here. Here we go. Oops, too much. There we go. Oh, there we go. Okay. Yeah, okay. So here is, oh, I got my laser here. Here is the function x cubed. Sorry, that's not blue. Maybe I should just use blue. Here we go. Here's the function x cubed. Oh, nice. I have a blue laser. That's x cubed. Now, if we switch the inputs and outputs, what we end up getting is we end up getting this function, cube root of x. So it's very, very similar, except it's reflected. And that's what I talk about in the next slide here. Let me pop to that. Here we go. All the inputs and the outputs are switched. And so what you get is you get this geometric reflection. The only values that don't change are the ones where the input and the output are the same. What does it mean for the input of a function to be the same as the output? It means x is equal to f of x, right? This equation is saying the input is the same as the output. Well, if the input is the same as the output and I invert the function, nothing's going to change. Those points where that's true, those are not going to go anywhere. And those are exactly the points on the line y equals x. And that's what's right here. I'll use green. Right here. So all the points on that line go nowhere through the inversion process. They're fixed. They're fixed on that line. And because of that, we can basically say that everything else gets flipped. So this is the graph of x cubed. If I want to graph the inverse of x cubed, I'm just going to reflect it about the line y equals x. That's exactly what happens. And this holds for any invertible function. So if you know your function passes the horizontal line test, you can graph its inverse by reflecting y equals f of x over the line y equals x. And I love this about inverses because sometimes inverses can seem like they're difficult to work with, but at least graphically, you can easily see what they look like. Just reflect it across that line. Wait, here we go. Reflect it across that line, y equals x. Another cool thing, if you're following what I'm saying with this means that the horizontal line test, where is it? There you go. The horizontal line test is really just a vertical line test for potential inverse functions. That's really all it is. So the horizontal line test is a vertical line test for possible inverses, right? Before the inversion, because if you reflect a vertical line through y equals x, it produces a horizontal line. So if I wanted to reflect this line through the line y equals x, what I'll get is this. So rather than try to invert the function and then sketch it and then do the vertical line test, you can just do the horizontal line test, and that'll tell you if it's a function, or if the inverse is a function. Pretty cool. Okay, next bit, we get the cancellation equations, and these are like everybody's favorite part of inverse functions, is canceling a whole bunch of stuff out. And remember, like I said in the intro, there's an emotional component to doing mathematics. So one of the best parts is when you get to cancel things, because it just cleans things up, and that you should have this like satisfying feeling of that cleanliness resulting. Cancellation equations are lovely. So here's what they are. Let's say you've got a function, and the function f inverse will be its inverse if and only if these two results hold. These two results hold. So you have an inverse if and only if these two things hold. In particular, f inverse of f of x equals x for every x in the domain of f, and f of f inverse of x equals x for every x in the domain of f inverse. That's why they're called the cancellation equations. In essence, it's kind of like the f inverse and the f are canceling out, are canceling out, and the f and the f inverse are canceling out, and you're just left with x. All right, so what's going on intuitively with this? So intuitively, remember that inverse functions undo the process of a function. So if you compose a function with its inverse, what you're going to do is you're going to apply the rule of the function first, and then you're going to undo the rule of the function next. And so what happens is you end up where you started. No change, right? You ended up with the thing that you put in initially. You perform the operation first, then you undo the operation second, you're back where you started. No change, right? And this actually works for any order. I'm sorry, for either order. So not just doing the function and then its inverse. If you perform the inverse operation first and then the forward operation, it'll also cancel out. So it's kind of like saying if you start by doing this and then you do this, you're going to end up where you started, right? If I start here and I go backward and then I go forward, I'm right where I started again. So everything cancels out. Everything cancels out. The other cool thing is that because this is an if and only if statement, it's an equivalence statement, which means this is an equivalent definition of an inverse function. So your function is an inverse if and only if these things hold. And what that means is that we can use these cancellation equations to check or to verify that our function is the inverse of another one. So in other words, if I've got a candidate for an inverse and I'm not sure if it's an inverse or not, I can compose it with its original function and everything should cancel out. If it doesn't cancel out, if there's like something else at the end, then they are not inverses of each other, not inverses of each other. So we're going to use this right now, actually. Okay, so this one I want you to try on your own, and then we'll do it together. So this one says, use the cancellation equations to verify that the inverse of f of x, which is this one from earlier, verify that the inverse of that is this function by using those cancellation equations. So first, think about how you would start this process. What would you do first? All right. Now, say something out loud to yourself about how you would proceed. What would you do first? Just say something out loud to yourself, to your dog, whoever. Okay, and now try to work it out on your own. Perform those calculations, compose those two functions, simplify, and see what you get, and we'll do it together. All right, let's try it on our own. Let's try it together. Okay, so we've got both calculations here. First, note that the domains of both of these functions is all real numbers, so we don't have to concern ourselves with domains or ranges or compatibility or anything like that. Everything's going to work out great. Now here's what I'm going to do first. I'm going to take f of x, which is this, and I'm going to put it into f inverse of x as the input. So remember, f inverse of x says to take the input, subtract 2, and then cube root. So I'm going to plug f of x in as the input for my inverse, and then simplify. What is f of x? F of x is x cubed plus 2. X cubed plus 2 minus 2, the 2's will cancel. And then x cubed cube rooted cancels out, and you're just left with x. There you go. So that's good. So basically, if we perform this thing first, if we cube and then add 2, and then we subtract 2 and take the cube root, we end up with what we started with, the input, the initial input. Now do it the other way. So plug in f inverse of x to f. So same thing. What does f say to do? It says to cube the input and then add 2. Well, this time we're putting in f inverse of x, so it's going to cube this. Well, if you cube a cube root, they cancel out. So now we're just left with x minus 2 plus 2. The 2's cancel out, and you're left with x, your original input. There we go. Therefore, this verifies that this function that we computed for f inverse is indeed the inverse function of f. There we go. All right. Whew, okay, so that was basically the review of inverse functions. Now let's get to some calculus. So now let's get to the actual calculus part of this section. Derivatives of inverse functions. So now that we know about inverse functions, the next natural questions are these two. How can we compute the derivative of an inverse function? And do we need to, oops, come back. There you go. And do we need to compute the inverse explicitly to compute its derivative? So in other words, if I wanted to know the derivative of an inverse for some function, do I need to compute the inverse first, like find the formula for the inverse first, and then calculate the derivative of that? Or is there another way? So think about it for a minute, and we'll talk about it again in a minute. But think, what do you think the answers to these questions are? All right, let's talk about it. So first, we're going to need an important theorem because we're going to use this later on a couple of times. So for one, if your function is invertible, if f is 1 to 1, and it's also continuous, then its inverse is also continuous. So if you have an invertible continuous function, the inverse is also continuous. In other words, you're not gonna lose continuity through the inversion process. So if the thing you start with is continuous and you invert it, you're still going to end up with continuousness at the end of that. It's not going to like break the function or anything. So we're going to use that in just a moment here. In particular, when we prove this theorem. So this is the inverse function theorem, and this is a very, very helpful theorem. So I'm going to read it, we'll talk about it, you should ponder it for a couple of minutes, and then we'll prove it, and then we'll use it in an example. So here we go. Let's suppose that f is a one-to-one differentiable function with an inverse function f inverse of 1. I'm sorry, with f inverse. Let A be a point in the domain of f inverse, and suppose that this value is not 0. So kind of a mouthful, but f prime of f inverse of A is not 0. Then what we know is that the inverse function f inverse will be differentiable at A, and we have a formula for the value of the derivative of the inverse at A. So in other words, the derivative of f inverse at A is equal to 1 over f prime of f inverse of A. All right, that's a mouthful. That's a lot to process. So what I want you to do is stare at this for a minute, read it to yourself a couple of times, and just try to parse out the pieces. Read through it carefully a few times. All right, now I want you to say something out loud to yourself about what you just read or what you're thinking. It could even be like, holy cow, what does this even say? Just say something out loud to give your brain that feedback, and then we'll talk about it. All right, here we go. So again, you should read this type of thing out loud. Make sure you're taking note of each individual piece because there's a lot of hypotheses here. There's a lot of things we're supposing in order to get this result at the bottom. A bunch of things. One, we're supposing that f is 1 to 1, so it has to be invertible. We're also supposing that f is differentiable, so we want an actual differentiable function. We're also supposing that this value is not equal to 0. The reason for that is then if it was equal to 0, we'd be dividing by 0, and that's highly problematic. So can't be 0. And if we have those three conditions, the function's invertible, it's differentiable, and that value is not 0, then we can actually evaluate the derivative of the inverse at that point. The derivative of the inverse at that point. All right, so this is important because what this does is it allows us to compute the value of the derivative of an inverse without explicitly computing the formula for the inverse first. And that's a powerful tool because if you don't have to go through the inversion process to get a result, that would be nice. That would save us a lot of pain. And this is saying that, hey, you don't have to go through the whole inversion process. You just have to know the value of the inverse at a point. So if you just know the value of the inverse at a point, maybe even by inspection, right? Just inputs and outputs inspection, then you can compute the value of the derivative of the inverse at that point, right? What's also very cool, and this is something that some of you will see in a later math course maybe, if you know that your derivative, that f prime, the derivative of the original function, if you know that it's non-zero for any x, then this theorem gives you an explicit formula for the inverse, which is amazing. This gives you an explicit formula for the inverse if you know that your derivative is never 0. All right? Okay. Let's look at the proof. So this is an important theorem. We should go through the proof. The proof is a little bit hairy because there's a lot of like switching back and forth. So I'll try to explain it a little bit carefully as I go through. So first, let y equal f inverse of x. Just label it y. Since we know that f is 1 to 1, we know that f of y equals x. So this is just using the definition of an inverse, right? This is true if and only if this is true. Next, just for ease, we're going to label this value b. So we're going to call f inverse of a b, so that, again, f of b equals a, just by the definition of an inverse. All right, so nothing funny has gone on here. We're literally just giving things names so that we can work with them. All right, now, since f is differentiable at a, it's continuous at a as well. That's a result from Calc 1. So when you first learn about differentiability, there's this result. If a function is differentiable at a point, then it's continuous at that point. Not the reverse, but if it's differentiable, you get continuity for free. So because we know that f is differentiable at that point, it's also continuous at that point. And by that theorem we just talked about, that means that f inverse is also continuous at that point. All right, why do we need this? Well, consequently, by the definition of continuity back from Calc 1, that means that the limit as x approaches a of f inverse of x is equal to f inverse of a. That's the definition of continuity. Or put equivalently, using our labels, this means that the limit as y goes to b of y is equal to b. And really this is just a substitution, right? Now, there's nothing funny going on. Remember, f inverse of x is y. So f inverse of x becomes y. And f inverse of a is b. So f inverse of a becomes b. And then if we're taking the limit as x goes to a, that's the same as taking the limit as y goes to b. There we go. Okay, now we have this all set up. Now we can go through the calculation and get the formula itself. So here we go. If we substitute our labels and using the definition of the derivative, we get something cute. So here we go. What is the derivative of f inverse at a? Well, by definition, it's this, right? Good old Calc 1, limit definition of the derivative, the limit of the difference quotient as you approach that point a. So this you should definitely have memorized, the definition of the derivative. Except here's our function, the derivative of f inverse. Now we're just going to plug in all of our substitutions. So f inverse of x is y. F inverse of a is b. X is f of y. A is f of b. So we're just relabeling things. And now our limit is going to be y going to b instead of x going to a. All right. Now here's a couple cute parts. There's a couple cute parts to this proof, I got to admit. We're going to rewrite this fraction as 1 over its reciprocal. So like this is the fraction y minus b over f of y minus f of b. So if we reciprocate it and flip it, basically divide by its reciprocal, we get an equivalent expression right here. Now there's a reason we did this. There's a reason we did that, and here's why. The next step, we're going to move the limit operator into the numerator and the denominator of this expression. But the limit of 1 is 1, and the limit of this down here, well, what is that? What's the limit of f of y minus f of b over y minus b as y goes to b? Stare at that for just a minute and think about what that represents. That is the derivative of f at the point b. This is the derivative of f at b. And so this becomes this, f prime of b. But what is b equal to? Remember, b is f inverse of a. So we can substitute f inverse of a for b. And voila, there's the proof. Now we have that formula. So the derivative of f inverse at a is 1 over this expression. Pretty cool stuff, pretty slick. All of the hypotheses in the theorem were used here. They were all necessary. We needed that differentiability, we needed that continuity, all of that was used here. In particular, we would not be able to go from this step to this step without differentiability. Because remember, you can't put the limit operator in the numerator and denominator unless the derivative exists, or unless the limit exists, right? So in this case, in order for this limit to exist, that means f needs to be differentiable, which it is. We also need that derivative to not be 0 at that point, which it's not, because that was one of the suppositions, right? That was one of the hypotheses. That's too far back. There we go. But that's the proof. That's how we get the formula. There's another really, really cute result here. Leibniz notation actually makes this result much, much more elegant. And so I want to show you here just how much more elegant Leibniz notation can be. If we write y equals f inverse of x like before, so that f of y equals x, then we can re-express all of these in terms of Leibniz notation. So here we go. F inverse prime of x is equal to d dx of f inverse of x by definition. But what is f inverse of x? It's y. So now we're looking at d dx of y, which is dy dx. So this thing is dy dx. There we go. Now let's look at this other expression that was in the denominator, f prime of f inverse of x. That's a mouthful. What's f inverse of x equal to? It's y. So really we're looking at f prime of y. But what's f prime of y? It's the derivative with respect to y of f of y. So it's d dy f of y. But what's f of y equal to? F of y is equal to x. So f of y is equal to x. And now what we're really looking at is dx dy. So, very elegantly, Leibniz notation says that the formula given by the inverse function theorem is that dy dx is equal to 1 over dx dy, which is just such a beautiful result, right? Because it's kind of like saying, hey, dy over dx is the same as 1 over dx over dy. It's like literally flipping and multiplying. That's essentially what it's doing. So that's pretty cool, and I like that result. Okay, all that being said, let's use the theorem now. So here we go. Let's say we've got the function f of x equals 2x plus cosine x. See if you can find the derivative of f inverse at 1. And so just like before, what I want you to do first is just think about what you would do to start this problem. How would you start it if you wanted to compute this value? All right, now say something out loud to yourself, to your dog, to your friend, to your family, anybody or nobody about how you would start it. Say something out loud. All right, now try to work it out on your own. See if you can figure out this value, f inverse prime of 1. Remember, you only need the value. It's a little bit of a hint. All right, now let's do it together. Okay, so first thing is this. Trying to compute an exact formula for the inverse is algebraically impossible. So this function here, that function, you cannot algebraically compute an inverse for it. It is not possible to do so. This is one of the reasons the inverse function theorem is so useful, because we can't compute the formula. The formula is not something that you can do with algebra. You literally cannot do it with algebra. It's not possible. And that's because this is a transcendental function here. Cosine is a transcendental function, and therefore f is a transcendental function as well. However, it's clear that f is differentiable on the real line because it's a sum of two differentiable functions. So both of those are differentiable. Check. Additionally, check this out. We could compute the derivative. If we compute the derivative, we get this. 2 minus sine of x. So 2 minus sine of x is strictly positive. 2 minus sine of x is strictly positive. Remember, sine just goes between -1 and 1. So the smallest sine will ever be is -1, and the biggest it will ever be is 1. So that means 2 minus that is never going to hit, it's never going to be 0 ever, never going to achieve 0. So what that means is this function is strictly increasing. It's strictly increasing. It's always increasing. It's always going up. But if it's strictly increasing, that means it's 1 to 1. And so that means it's invertible. So it has an inverse. Whatever this function is, its inverse exists. It is an invertible function. We just can't compute the formula for it. It's invertible, but we can't compute the formula for it. However, we can still apply the inverse function theorem. We've got everything we need. We've got differentiability of f. We've got a one-to-one function, so we know it's invertible. We also know that, oh, where is it? That one expression, f prime of f inverse of 1, well, we've got to check that that's not 0, I should say. We don't know that yet. But we've got continuity, right? F is continuous because it's differentiable. It's differentiable everywhere, so it's continuous everywhere. Now all we need to know is we need to know the value of f inverse when x is 1. That's the one thing we don't know yet. So if you go back to the theorem, let me pull it up here, this one. We don't know this yet, f inverse of 1. And so we don't know if that expression is going to be 0. However, we can figure out what it is by inspection. So remember, f inverse of 1 equals x means that f of x equals 1. So when does f of x equal 1? And if you look at this result here and think about it for a minute or so, you'll realize that 0 is a solution to that. F of 0 is equal to 1. So if I plug in 0 here, I get 0. And if I plug in 0 here, I get 1. So f of 0 is equal to 1. Now, since f of 0 is equal to 1, that means f inverse of 1 equals 0. And so, yeah, this is what I was just saying here. All right? So now we can apply the inverse function theorem. One thing I want to emphasize here is that, here, we're going to see it down here actually. Just because f inverse of 1 is equal to 0, let me write that here, f inverse of 1 is equal to 0, that doesn't mean that this expression is going to be equal to 0. Not necessarily, but we're going to find out right now, right? So f inverse of 1 is 0, so this becomes f prime of 0. What's f prime of 0? Well, we computed that, right? This is f prime. So f prime of 0 is 2 minus sine of 0, which is 2. There we go. And that's all she wrote. That's all we needed right there. Let me erase some of this stuff. There we go. That's it. So what we know is that the derivative of f inverse at the number 1 is equal to 1/2. So we were able to compute this. We were able to compute the slope of the tangent line to the inverse function at the number 1. And that slope is 1/2. And we were able to do this without a formula. We didn't have to compute the inverse itself. We just had to get one value of the inverse at one point, and we were able to figure this out, which is really cool. All right, so that's the usefulness of the inverse function theorem. And so now let's play. So now that you've watched this, what we're going to do is during the activity time, we're going to do an activity related to this. You're going to work in groups. I'll come around and make sure everybody's getting things, and I'll be there to answer questions and help you all out. So I'm really excited about that. But I think I'll stop here. Thank you all for bearing with it. I know that some of these lectures are a little bit long. This one's coming out at basically 1 hour, but you can always watch them at double speed if you want. Oh, wait, hold on one second. There we go. There we go. Now you can see me better. You can watch them at double speed. You can pause them. You can watch them with friends. You can watch them with classmates. But they'll always be here for your reference in the future, as well as the slides, okay? So on that note, once again, thank you, and I will see you next time.